Okay, so Colin asked me to demonstrate, I think, two features, right, Colin? Time since transition and adjacency.
Yeah.
Okay, so the first one, I have to admit, he just asked me to do this an hour ago. So I came up with an example that's hopefully not too complicated, where I took the existing exercise 6 model and I wanted to add some this is contingency on, the probability of a transition depending on how long it's been since another transition. So I took our simple model and I added a couple of things to it. I'll probably start with the transition pathways. But the dynamic that I added to the model is that when you apply timber harvest now, rather than going to the young deciduous, it goes to a post-harvest state. And the idea is that to get back onto the successional trajectory, there has to be some kind of succession that takes, that maybe establishes the young conifers on that stand. Again, I totally made this up, so it's armchair theory at the moment, but just to demonstrate, I think, the simple dynamic. So in this post-harvest state, there's two things that could possibly happen. You can have a succession with a low probability, and you can have planting. But I wanted the succession, so the succession is what gets you out of this post-harvest state. I wanted the succession to be contingent on planting. So this is kind of this idea of contingency on time since planting to determine whether succession can happen from post-harvest deciduous to young deciduous. And so the way I did that in this model is there's in the transition multipliers, there's some hidden fields that I've kind of exposed. And I'm just going to make this a little bigger so we can see all of the fields. You see I've added a few fields. So here's that multiplier that you guys set up in an earlier exercise, but you'll see there's a few rows that I've added. So first of all, these two rows, what I'm saying here is that if you're in the deciduous post-harvest state class and you've had a planting transition, this is the time since transition group or type that we care about. If you've had planting within the last 9 years, so between 0 and 9 years prior to this, your succession probability gets multiplied by 1. In other words, we turn on the succession probability. But if you haven't been planted, so if it's been more than 10 years since you've had any planting, your succession probability gets multiplied by 0. So what I'm saying with these two rows is that for succession to happen from the deciduous post-harvest to deciduous young is you have to have been planted within the last 9 years. Otherwise, succession can't happen. Any questions so far at this point? Okay. And then the only other thing that I added as well is there's no point, if planting is good for 10 years, there's no point planting repeatedly year after year. I have limited resources for planting. So once I plant, within 9 years of planting, I turn off planting. I apply a multiplier of 0 against planting. So I say no planting within 9 years of planting. And once it's been 10 years since I last planted, I can apply planting as well. And then the next thing I did is just to kind of show different scenarios. In this scenario, I set the planting target to 0. I'm not going to do any tree planting. And then I added a couple of scenarios. One where, we're cutting 3,000 hectares per year. So what if I apply planting to targets? What if I apply planting to 1/10 of what I'm harvesting? And then finally is what if I apply planting to 2,500 hectares per year? So almost all of it. But remember, I think I set the bar. I would have changed this probably. I've already run the model and it takes a while. One thing I did is I kind of set the bar for planting success to be pretty low, only 5% of 5% annually if you've been planting of succession. So chances are, you know, without a lot of planting, you're going to stay here in this post-harvest state. So I ran those 3 scenarios and they're already in the results. So a couple of results that we could look at. First of all, let's take a look at the transitions. And maybe I've been talking for a while, I should pause. Is there any questions so far? Okay, so here's my 3 scenarios. The blue is no planting. The red is planting 300 hectares per year. And you can see here, there's the 300 hectares per year of planting. And the green is planting 2,500 hectares per year. And you can start to see, it's a little harder to see here, but maybe if we just change it from 2014 to 2033, you can see, and I'm just going to turn on off the min and max. I'm sorry, not min and max, no ranges. You can kind of see that the scenario that does more planting has more succession happening. Okay, so that's that planting, adding more planting is allowing that successional transition to happen. A couple of other outputs that we could look at is we could look at the states over time. And so, again, it's a little harder to see because of all the variability. If I turn off the ranges, the scenario, you know, the scenario that has the least of this post-harvest is the one where I'm doing most planting, because I need to plant in order to be able to get out of this post-harvest state. So that's a big difference that you can start to see once I start planting more. And then the other thing that you can see as well is, say, a map of how long has it been since I planted over time. And we've got for 2020 and 2033, and kind of the gray area. So this top scenario here is a scenario that had no planting at all. And the scenario labels are not on. We should probably put them in. Show scenario name. Okay, so this is the scenario with no planting. Here's a scenario where we're planting 300 hectares per year. So you can start to see the time since planting for each simulation cell on the landscape. And then here's a scenario where we apply 2,500 hectares. So you can see the color codings are kind of the time since planting that has been applied to these simulation cells. That's hopefully, I mean, you know, it's a bit of a more complicated feature, but hopefully you get a sense of how you could use this approach to set kind of contingency on the history of a cell for the future probabilities of transitions.
Can I add something here, Narco? Oh.
Yeah, go ahead.
You might be curious. The origin of us wanting time since transition in the model goes way back to the very beginning of these simulations. Like I'm talking about 20 years ago, where the main concern people had, and it applies to Australia, has to do the buildup of fuel ladders under mature canopies of trees. So we have old growth forests, and if those forests don't burn regularly, young conifers and oaks will build under the canopy. And then the idea was due to fire suppression. So if you have thinning operation or regular prescribed fire, you keep down those fuel ladders and they don't kill the overstory, basically. And the idea was, how do we capture that phenomena in the models? And it has to do, as soon as you do a prescribed fire, you thin the understory, then the clock starts ticking. And if after 30 years of not doing that, so you haven't done prescribed fire, then suddenly you have a fuel ladder problem that could kill your canopy. And that's, for ponderosa pine, that's the feature that created this option. And as you can see, it became more complicated over time. But that's the origin of this thing, is I haven't done this thing that's beneficial, and I haven't done it for so many decades, and suddenly I'm like, oh crap, something bad's going to happen. The ability to measure that is what caused this feature to be created.
Okay.
Yeah, that's another good example of it. You want me to show the adjacency multipliers, Colin?
Yeah, sure. These are just two features that we've mentioned in the course and never covered, and I felt a little bad that we hadn't kind of showed them to you. I'm starting to remember now why we saved them for not being part of the intro course, because they're a little bit tough to get your head around at first. But I think the point of this was to show you that these levers do exist once you do want to think about this kind
So
of.
this is a model for a national park in southern Ontario. I think it's actually the southernmost point in Canada, right, Colin? Point Pelee National Park.
Right. Yeah.
It's a wetland system, and we're looking at the spread of one of them, quite an invasive species called Phragmites, a wetland invasive, and the other one is cattails, spread of cattails in this area. And so the way we modeled the spread of Phragmites is using the adjacency feature, the adjacency multipliers feature that's under this transition spatial adjacency multipliers. And so the idea is that, and it's actually become a little bit easier to do this since we developed this model, but essentially what we're saying here is that this Phragmites invasion transition group cares about how much Phragmites is in the neighborhood of a cell. If you're worried about what is your probability of getting invaded by Phragmites, it depends on how much Phragmites there is within a 60-meter radius. I can't remember the resolution of this model. Let me just take a quick look.
It was 10 meters.
Initial conditions. Why am I not? Oh, right, because this is the just that scenario here. So we were running at cell size. I think this is 25 meters. 10 meters. You're right. Or no, 20 meters. I think this is 20-meter resolution. 20 by 20, 400 square meters, 0.04 hectares. I think it's a 20-meter resolution model. So essentially, the neighborhood that we're looking at here is, if it's within kind of the rook neighborhood of 3 neighbors, and then you're going to capture some of the diagonals within that. And what we're saying here is that as the number of neighbors, so there is some probability that Phragmites invasion might happen, and these are multipliers on the base probabilities. There is some probability that Phragmites invasion might happen if you have no neighbors. But as the number of neighbors that you have increases, your probability of Phragmites invasion increases quite a bit. So if most of your neighbors, I think it's actually just at 0.8, or actually a 60 neighbor value, right? So if within that 60-meter radius, most of your neighbors have Phragmites, your probability is much higher. Your probability is multiplied by 40 times of getting invaded relative to almost very low probability if you have no neighbors with Phragmites. And we actually calibrated this model using a historical data set. So now we've got 3 scenarios, and we can take a look, for example, at the cover type over time. So we can see that as you start to get more Phragmites on the landscape, this is kind of a calibration over the historic time period. As you start to get more Phragmites on the landscape, the rate of spread increases. It's kind of this exponential pattern, right? The more cells that are out there, the more spread you're going to have. And then we also, up to a certain point, you see it kind of leveling off here because the amount of available area for invasion starts to get reduced. And then we added 2 scenarios, one where we apply no management, and one scenario where we applied sort of a base level or budget for different management activities. That's the green one, so you start to see a reduction in Phragmites over time. And then initially with the taifa, the cattails are also increasing over time, but then they start to decrease as the Phragmites starts to take over. And we've also got some maps that show those results. So, and maybe I'll just reduce the number of rows. Right, so this is 1959 where we start the historic simulation, And the Phragmites is either orange or red, mostly orange. So we distinguish between rooted and floating patches of Phragmites. So you can see that by 2015, there's these orange patches. Let me just make this a little bigger even. So these orange patches of Phragmites have grown over time. And then if we project forward 10 more years, so here's a scenario, oops, I'm not sure why that got jumpy. So here's a scenario where we projected from 2015 to 2025 with no management. And again, you can see that effect of the neighbors where existing patches start to fill in and where areas that were smaller patches, again, fill in and start to expand. And you can see that happening throughout. And you do see some new patches appearing, but most of the new Phragmites is happening through this spread. And then here's the scenario where we applied management. And that management's being targeted, I didn't show it in this example, but is being targeted towards specific locations. And some of the things that you can do in your model is you can say things like target the edges of patches, and you can say things like target smaller patches before you target bigger patches to try to sort of eliminate new sources of contagion as a priority as well.
That's great. Yeah, if you go on our website, I'll have a link at the end of the talk, course, a bunch of links, but one of them is to our publications. But you'll see in there, there's Leonardo in particular, and he's done some of it with Louis too, but he's done a lot of work with invasive species and modeling it and looking at we have several examples in STSIM, a number of them published of that kind of work. It's really interesting work, I find. Just one other thing to share about that Point Pelee example. I wasn't going to show it, but now that you mentioned it, I thought, okay, well, I will. But this is the actual state and transition model behind. These are the box and arrow diagram behind that model. Not to get into the details, but you can see it's sort of modeling open water and Typha and Phragmites in different forms. But the thing that's interesting about this one is this is the only example I know of us doing 3D modeling. So getting, we've done other wetland stuff, but this was a model where we were actually modeling the third dimension of depth. And we did that by using the depth classes being strata. So we actually had different strata, which were different depth classes. And so the dynamics of the Typha and the Phragmites are different. In fact, once you get to a certain depth, you don't see any Phragmites or Typha, right? And as you get shallower, the dynamics differ. So we were able to pick up the differences in that. And in fact, if I can go over here, we could look at some scenarios here. Here's different scenarios of different management treatments, and this was the one that I love. We were actually able to model what would happen if you changed water levels in the wetland through, changing the dikes and the water control. And so we were able to look, okay, if you shift the water level, it means that the state of any one cell is moving from one strata to another. It's moving across depth classes. So this is kind of a really unique model in a way of us being able to capture this third dimension of depth if you have systems that you're thinking of that are also kind of similar. That's an interesting side.
Colin, this actually applies to the GPK with the depth of water with prolonged flooding that kills differentially the eucalypt, and if there's ponding is differential, and it may also affect the invasive. So something to keep in mind. It's really interesting.
Yeah, if you have a separate hydrology model where you can predict every time step out into the future, maybe with uncertainty, what each cell's water depth would be. If we had that kind of model for Point Pelee, we could have brought that in and used it to drive these transitions between depth classes. So that's a way you can integrate sort of hydrological modeling into this if you can capture the effects of change in water table or water depth on your vegetation. Any questions before I move on to the, yeah, is that you, Anna?
That's me, yeah. Just on that note, Louis, yeah, it got me thinking about how do you put in the link between strata in the UI, in that transition pathways part? How do you show that arrows between strata, or is that just the same as between state classes?
Yeah, did we have that in any of our examples that we sort of gleaned over? Trying to think if I have.
I think the Hawaii model had transitions between
Right.
music and.
Right, so maybe if I just quickly bring up the Hawaii model. Yeah, it's gone here from my list. Let's go down to the, now you know about sub scenarios, I'll go down and look at the pathways there because it's easier to look at. Actually, I'll just make this not read only again so you can see them better. But if we go,
my colleague is looking for that. Oh, here you are. Okay.
This is what a transition looks like on the diagram that's going off to another strata. This is a transition coming in from another strata. This is another one going out. So that's how we visualize it. But if you go over here, you know, so you can create them here. If I actually look here, there's a transition here. It's going from this class to, this is the model for, I'm on the dry strata pathway diagram, and I've got a transition here. One of the optional columns is to send it to another strata, right? So I'm sending it from its dry state stratum to the mesic stratum with this transition type called moisture zone shift. So that's how we do it. We bring in this optional column and we tell it to go to a state class on another strata. That makes sense?
Oh, tomorrow, I did that in the model we're going to see tomorrow, except I did it between the eucalypt forest and the wetland using the two vegetation type. But what you're saying is that it could be two to anything, including an ecozone. That's not necessarily an ecological system.
Right, it could be to any strata. I mean, I think, yeah.
Cool.
Yeah. Okay. Have a good afternoon, evening, and actually it's now past midnight for me, so morning. So we'll see you all tomorrow. Thanks again.
Thanks, Colin.
Okay, bye.
Thank you.